So we're going to be recording this part of the session. If anybody has any objections, please say so now. Okay, so to kind of round out the topics of the unit, up to this point, we have been talking about mostly and mainly we've been talking about point charges, which are charges that are located in somewhere in space. They are at a fixed point that really has no geometry, no geometry or any sort of length or distance or area or anything like that. It's just a point charge, a point in space that has a certain charge. And so now we're going to kind of close things out, talking about situations where we have objects that have a certain geometry, but these objects are charged. So for example, instead of talking about a point in space that has a charge, well, let's imagine that now we have, for example, a line in space that has a certain charge, and what type of electrical fields does this line generate at any point? Or let's imagine that we have some sort of object that has some sort of surface, and this is electrically charged and is generating an electrical field. So what happens there? And kids, we need to dust off our integrals or our integral calculus for that. And to motivate you guys, we're going to have some bonuses there. So we're going to see three examples that we're going to be talking about in today's session, which have to do with these three situations. We're going to talk about what happens when we have a charged line, a charged ring, and a charged disk as three examples. And this here, as you know, obviously is charged Thor. And why am I putting the hammer there? Just remember that whenever I put the hammer, it means that remember, you have to, or we have to use the tools that we have been given, those that we know and those that we seek and find to solve problems. Okay, so you've already taken your physics courses and you've already taken your calculus courses. And so now all of that knowledge we should be able to apply. Okay, now let's talk about this situation before we get into the math of it. But we've been talking about point charges. So we've got charges, we've got a charge in space that's, for example, a positive charge. Let's call this Q1. And we know that this electrical charge is generating an electrical field, right? And how is that electrical field going to be? What's going to be its characteristics? Anybody? Remember, that's going to be questions in the exam. Okay, go ahead.
Outwards.
Going to be going outwards. Perfect. It was Carmina. Perfect. It's going to be going outwards. What else do we know about the electrical field?
As you get farther away from the positive charge, it becomes less the power. Is it power or the field?
The electrical field, correct? But it's very correct, Lucia. So it's inversely proportional to the square of the distance and directly proportional to the charge. So the farther we are, the less the electrical field is. And it's going to be proportional to the charge. But now imagine that instead of having a point charge, then now let's assume that I have a line. I have a line that has a certain length. And this line also is positively charged. All this line is positively charged. And this is also generating an electrical field. Would you agree? This is also generating an electrical field that for all effective purposes, it's also going outwards. Okay? It's also going outwards because it's positive. Would you agree with that? It's going outwards because it's a positive. It's a positive charge. Now, we know that there's a relationship that defines the electrical field for this point charge that says that E equals K multiplied by the charge, which in this case is Q1, divided by the square of the distance. So like Lucia was saying, if I put myself here at a certain distance R, then the electrical field is going to have this magnitude, right? But what happens if now we have a line charge or a charged line? And I want to locate myself here, in this point here. And I want to know, what is the electrical field do to this line charge at this point? Okay. It's not going to be this expression here because this is for a point charge. This is a bit different. And this is where some of the integral calculus comes along. Okay. Questions? Is the situation clear? The difference between both of these? Now imagine that instead of having a line, now I have a ring. And I'm drawing it red again because the ring is charged. And also I want to know what the electrical field is at a certain point that is at a certain distance from the ring. And now let's also imagine that instead of a ring, I have a disc. And I also want to know, what would the electrical charge be at a certain point that's located at a certain distance from the disc, and so on and so forth. I can have different geometries, and I want to know what the charges are. How do you think we could approach finding these expressions? Anybody? Let's see if we can link up some knowledge. How do you think we could approach finding the expressions for each of these situations and any other situation that I might have where we're not talking about a point charge? Ideas? Anybody? Interesting. Okay. What is an integral? Can somebody tell me what an integral is and what's it used for? I'm going to put this on YouTube, and I'm going to say that this is the Industrial Engineering Global Program group.
An integral, professor, it's used to find the area under a curve between some intervals.
Yeah, that's good. Let's start with that, Pedro. It's used to find the area under a curve between a certain interval. And how do we find that area under the curve? Or what does an integral do to find the area under a curve?
It's a symmetry.
Perfect. Perfect, Pedro. You demonstrated that you do remember your integral calculus. It's a sum. It's a continuous sum of all of the little small points along a curve. It's basically what an integral does. So very, very good, Pedro. And so let's try to follow this logic here, everybody. Let's assume that I have this line, and instead of looking at the whole line, I'm just going to look at a very small portion. I'm going to use another color. Instead of looking at the whole line, I'm going to look at a very small portion of the line. A very small portion. Infinitesimally small. And since that portion of the line is so small, I can consider that the electrical field of this small point is equal to this. The contribution of this small point of the electrical field, E, is equal to this, because since it's just a small point that I'm taking in the line, then it's equivalent of it being a point charge. Okay? And so if I know what the electrical field is for that small point, that's a differential. And so if I add up all of them along the line or along the geometry of the object, I can find the whole effect that each of these very infinitesimal small points contribute. And so basically, if I do an integral from length A to length B of the effects of all of these small points that I have defined, then I can therefore find the whole contribution of all of the points along the line. The same thing happens with the ring. I can take a very small portion of the ring and say that it's equivalent to a point charge. And then I'm just going to add all of these along the length of the ring, and I can find the contributions of the electrical field at a certain point. The same thing can happen with the area. I can find a certain ring, which I've already defined previously, and I can say that the electrical field of the ring is equal to this, and just add all of them along the radius from 0 to r, and I can find the whole contribution of the disk. And so the integrals help us when we have a continuous situation where I have a charge that is distributed evenly along a certain surface. If I consider one point in that surface to be like a point charge, I can add up all of the contributions using an integral, and that can help me find the whole contribution of the object. Okay?
Professor,
Yes.
I sent you a
Yes,
message.
I saw it. It's okay.
Okay, thank you. I will connect when it is possible again. Thank you.
Okay, thank you. Okay. Okay, so this is basically where we're going. Before we go and see the examples, questions with this? Okay, I'm going to clear I'm going to clear this, and let's talk about now let's talk about the line. So there is a concept that is important to note here. And this concept is that when we were talking about point charges, well, basically the point charge had a charge Q, right? Because all of the charge was located in this infinitesimal small point in space. And so now the charge is distributed, and we're going to assume it's distributed evenly. Okay? If it weren't distributed evenly, then that's another situation. But we're going to assume that the charge is distributed evenly along a certain object or surface. And so now then there's a new concept that we're going to be adding or talking about, which is this concept here that's called lambda. And lambda represents the density. The density of charge. The density of charge, which basically means that lambda, in this case, instead of talking about charge, we're going to be talking about charge that, in this case, for a line, it's going to be charge per length or charge per length, meaning that if I have a line that's 1 meter and the whole charge is 2 columns, then the density is going to be 2 columns per meter. Okay, so the density represents this relationship between charge and, in this case, length. And there are going to be other types of density with areas and stuff like that. Now, what we're going to do is that we're going to grab a little piece here of the line, a small piece of the line, and this small piece of the line is going to be a very small portion that is at a distance x from a point that I'm analyzing, which is this point here where I want to find the electrical field or the effect of the electrical field of the charge. And so remembering what we know about differential calculus, if we have lambda, and this is a relationship between the total charge and the distance or the length, well, this is also going to be equal to the small portion of charge, or dq, divided by the difference in the length. So if the whole line is of length L and the whole line has a charge Q, then a small differential of line has a small differential of charge dq. So we can also establish the relationship that lambda is equal to dq divided by dx. And therefore, the whole charge Q can be represented as lambda, in this case. I'm sorry. dq, which is the differential of the charge, is equal to lambda multiplied by the differential of the distance. Okay, this is basically what we have here. And now, if I'm looking at a point here in space that's located here, and I want to find the contribution of the electrical field that's happening, basically this differential here is going to generate an electrical field that's going to be going outwards. I'm going to draw that in green. And this electrical field is going to have two components. It's going to have the component that is going this way, and it's going to have the component that's going this way. Now, the component that's going horizontally is actually going to cancel out, because if I grab another differential on this side, that same differential is going to go this way, and we're going to have a charge going this way and a field going this way and another field going upwards. The fields that are going to be horizontal, these are going to cancel each other out. The fields that are going vertically are going to add up. And so the only component that I'm interested in is the vertical component. And that vertical component is going to be given by the cosine of the electrical field. Now, how do I calculate the cosine of this angle? The cosine of that angle is going to be, according to the information I'm given here, it's going to be equal to z, which is the distance from the line to the point, divided by the hypotenuse, which in this case is a distance r that we're defining from the differential to the point. And this is actually this that we have here. Okay, and so the differential of the electrical field is going to be given by the formula we know, which is K multiplied by the charge, which is given by dq, divided by the square of the distance, which is r, and multiplied by the cosine of the angle. Okay, this is going to be the differential, which is that small part of the electrical field that we are analyzing for this small section here. And now, how do we find the total electrical field? Well, we are going to do an integral of this from one point to the other. And in this case, we're taking the reference point here that's located at a distance x. That's going to be our reference point. So anything going to the right is going to be positive. Anything going to the left is going to be negative. So we're going to go from minus a to b and doing the integral of all of the elements that are variable, which in this case is dx. R squared is going to be multiplied by r, and this is going to give us r to the 3. And in the end, r is equal to the square root of z squared plus x squared, which is this element, this component that we have here. Once we solve the integral, and I'm going to talk a little bit about a bonus there that I'm going to ask you guys to do. Once we solve the integral, we get this expression here. I'm going to erase this part here. We get this expression here that is the expression that is going to represent the total electrical field in this point that's located at a certain distance z from the bar. And it's going to be an electrical field that's going in this direction, which is this one here. And so we notice that that electrical field as a difference from the point charge, that electrical field is going to contemplate or consider the two distances, meaning the distance from the point to the left and to the right. It's also going to consider the distance z that goes from the line perpendicular to the point. And it's going to consider lambda, which is going to be the distribution of the distribution of the charge for the density of the charge divided by the distance. Okay. If we consider a line that is infinite, so it's not a line that has a point A, point B, it's not a fixed line, it's an infinite line. If we consider the infinite line, which would mean that this integral would go from minus infinite to infinite, then we get a simplified expression, which is this one that we have here. And it's only going to depend on lambda and in this case, z, which is the distance to the bar. Okay. Now, I'm going to give you guys a bonus relating to the integrals. Okay. This is going to be a bonus that is not going to be delivered via the discussion forum. It's going to be delivered via email. Okay. And so, how do we get from here to here? Basically, we've got an integral here. So how do we solve that integral? Okay. And this is out of your integral calculus class. How do we solve that integral? So I am going to give you the bonus. This is going to be a quick bonus. It's going to be for today, before midnight. If you send me an email where you solve that integral, but you have to do it by hand. You have to do it by hand, and you take a picture, and it has to be clear. If you solve that integral with the whole and complete procedure to get to this, I'm going to give you some extra points. Okay. It has to be delivered via email before midnight. And I'm going to ask for you to send it via a PDF. So if you take the pictures, do a PDF. Don't send me the bunch of pictures. Okay. And I'm going to give you some extra points for that. By the way, this isn't because I can't solve that integral. Actually, I'm going to record a video where I'm going to solve the integral. I'm going to record it this week and upload it. So you have that as a reference. Okay. But I'm going to give you the opportunity to do a bonus there. Okay.
Professor, the bonus is by houses, right? Or individual?
No, that's it. It's going to be individually.
Okay.
It's going to be individual. So I'm going to give the bonus individually. Okay.
Yes.
Okay. Some of these bonuses are going to be individual. So this is individual. So just if you do it, send it to me via email. Okay.
Professor, and you said we have all day to
all
submit it?
day until midnight. Literally until 11:59. Okay.
What if we are not able to turn it in? Can we do it like later on?
Well, this is a bonus. So this bonuses have time limits. There's actually going to be another 2 bonuses that are going to be similar to this one, but which is actually the ring and the disc one. So you're going to have other opportunities if you can't turn in this one.
All right, perfect. Thank you.
Okay. So let's do a couple of examples of how we use this before we move on. Okay. I'm going to clear the drawings here. Okay. Now it says, find the electrical field generated by a 1 meter line with a uniform charge of 1 microcoulomb at a distance of 1 meter perpendicular to the center of the line. Okay. Now let's see how we can contextualize that. Well, first off, it's a 1 meter line. Let's start marking these things here. So it's a 1 meter line. The length of the line is 1 meter. Okay. It is a uniform charge of 1 microcoulomb. Okay. So the charge, the total charge of the line Q is 1 microcoulomb. Can somebody, oh, and that's one information. The other is that there is a point that's located at a distance of 1 meter and it's perpendicular to the center of the line. So actually what we have here is that we have a point that is located at 1 meter perpendicular to the line. So we've got a point here. This is the point I'm interested in. That is located 1 meter from the line. And I want to find the electrical field at this point. Okay, so basically what I want to find is I want to find the electrical field at this point here. Okay. And we're going to use those expressions to find it. Now, help me out with a few things here. Can somebody tell me what the value of lambda is, or how we could calculate the value of lambda?
Charge divided by length.
Correct, JC. So basically, lambda is charge divided by length. We know that the total charge is 1 microcoulomb, and the total length is 1 meter. Okay. And so the lambda is 1 times 10 to the minus 6 coulombs divided by meter. Remember the multipliers, okay? So that is lambda. That is lambda. We know the value of Z. The value of Z, what's the value of Z?
1 meter.
1 meter, perfect. Let me just, 1 meter, perfect. What is the value of, what are the values of A and B in this case?
I would say that both of them are 0.5, I think.
Correct, correct, Omar. Why? Because the point is located here exactly in the middle. So if it's located exactly in the middle, that means that this is the reference. This is the 0 reference. So we've got 0.5 meters going this way. And we've got another 0.5 meters going the other way. Now notice that I could give you variations of this problem where it's not located exactly in the center, okay? And we would need to see that. And so A and B are these two values. They actually have the same value. B is 0.5. And A is 0.5. I think we've got all of the information we need, right?
Professor, I have a question.
Yes, please go
So
ahead.
because we're located at 0, A is negative 0.5, but when you already did all of the integral, it ends up being positive.
Correct. That's a good observation, Lucia. So when we establish the integral, because we are taking the reference, the zero reference, the integral goes from minus A to B. Once we solve the integral and substitute the values, the A is just a magnitude. Okay, so that's a correct observation. In the integral, as a reference, it goes from minus A to B. But in the final formula or expression, we just use A and B because the signs have already been considered. And that would be part of the procedure. When if you do the bonus, you would find that in the by doing the procedure.
Okay, thank you.
Okay, can somebody please then do the calculation? We need to substitute these values here and find what the electrical field would be. Can somebody please do the calculations and give us, a few of you do the calculations. And let's see if we get to the same values, okay? Oh, and you already know the value of K. Remember that you know the value of K is the constant that we always use, okay? This is the 9 times 10 to the 9. Oops. Okay, so let's do the calculations as soon as somebody has it. And I want let's do this with the calculations from now on, because I need you guys to do the calculations. I'm going to ask each of the houses to give me the value you got. So give me values per house so we can verify. So each house has to do the calculations so we can verify that we've got that we did them correctly. Okay. Okay, how are we doing with the calculations? Anybody have it ready? Please.
Just give me a second.
Go ahead.
I have the answer, Professor. Well, my calculation.
Okay, let's see what you got.
I got
Omar.
8,050.08.
9,000, 90050, 9,050,
It is 8,000. 8,000.
8,050. Okay, let's please corroborate the, let me write it down completely. So 8,050, like that.
Yeah,
I have
0.08.
Mhm. Let's verify that,
Professor,
everybody.
I
One
have the
Mhm.
different ends. Okay.
Okay, wait, let's just give this an order. So this is one result that we got. Omar did the calculations. I want us to verify this. There was a comment and a question. Let's see, who wanted to ask a question first off?
me, Carmina.
Carmina, go ahead, Carmina.
The letter A, the value is 0.5 or is minus 0.5?
No, it would be positive. When we put it in the integral, we're going from minus a to b because of the reference. But once we use it in the formula, it would be the 0.5.
Okay, thank you.
I got a different answer, but I think it's due to the decimals. Me too.
What values did you get? Let's verify this.
I got 8,049.84.
Oh, no, that's fine. Oh, I thought you got 2
No,
or
no,
3
no,
or
no.
something.
No, I
No,
think
that.
it's for the
No,
decimals, like the calculator.
Yeah, no, that's fine. If you got, so you got 8,049.
0.84.
Yeah, we're
Yeah,
good.
me
We're in
too.
the same range. Who else got a value, Marisa?
Yeah, it was the same as Lucia.
Me too,
Okay.
same as Lucia.
Just a question. This is important. Question. Did you guys use 9 times 10 to the 9? Right? All of you did, right?
Yes.
Yes, I did.
Yes.
Yeah. Okay. So it's around. I'm going to do this. This is valid to do. Give me a moment. So we are talking about a range of around 850 newtons divided by Coulomb. Okay, around 8,050. That seems right. Good. And now let's assume now that we put, this is the electrical field that's at this point here. This is the electrical field that's going this way. Now let's assume that we place a negative electrical charge here. So we place a negative electrical charge at the same point that we're talking about, which is this one. And the negative electrical charge is of 2 microcoulombs, okay? And so now we want to know the electrical force that's happening. So we have an electrical field that's happening here. And so we've got a negative charge that there's going to be a force that's going to be exerted here towards the bar. Okay, we're going to call this force F. How could we calculate that force? Well, the force upon the charge is going to be equal to the electrical field multiplied by the charge, which in this case would be the 8,050 multiplied by the 2 microcoulombs. What would be the force then that would be exerted on that charge? Can you please do that calculation? Remember that remember the multiplier times 10 to the minus 6, the micro, okay? So we've got the 8,050 electrical field, and now we put a charge there. The force is going to be equal to the electrical field multiplied by the charge. What would be the force on that charge? Okay, let's see who's got the answer. Basically 2 times 8,050, but times 10 to the minus 6. So just add the multiplier there. What would we have?
Do we have to put negative or not?
No, we're just, because we're indicating that the negative only helps us to know where the force is going. Since the charge is negative, we know that the charge would be attracted to the line.
So basically we do the same, but just with 2 microcolumns. Yes. or no?
Again, Carmina?
Do we do the same, like the same calculation, but instead of 1, it's going to be 2?
No. This was problem 1. In problem 1, we wanted to find the electrical field that's produced by this line, and we just found it. It's this one. In problem 2, we're placing a negative charge here in the same point, and we want to know what the force is on this negative charge due to the electrical field of the line. How do we calculate that? The force on that electrical charge is going to be the electrical field that we just found multiplied by the charge, which is 2 microcolumns. And that's what we're trying to find.
I already have the answer.
Me
Go
too.
ahead. Go ahead.
Is
Lucia.
it 0.016?
I got the same.
0.016 newtons.
Yes.
Mhm. Okay, that would be the force that's exerted according to which is basically 8,050 multiplied by 0.000002. Okay, which would be the 0.016. Okay. So somebody else corroborate we've got 2 corroborations that it's 0.016. Somebody else corroborate, please.
I had the same result.
Yeah, I got the same.
Perfect. And so now what we found in 1 is that we have a line that has a charge, and that line is going to have an electrical field that it's generated. Now, if I place a charge in that electrical field, the force exerted is going to be this. Okay. And so this is an example as to how we can do how we can find these, or how we can also establish the effects of electrical fields, but not necessarily when the object is a point charge or and has a certain geometry. Okay. And remember that, you guys, if you solve this integral, you're going to get some bonus points. Okay. We're going to take a 10-minute break and then come back and continue. Okay, so questions with this problem before we move on? No? Okay. I'm going to clear this in 3, 2. Oh, and all of this solution, we're recording the session, but this is also going to be in the PowerPoint. Okay, the updated PowerPoint that I'm going to upload to Blackboard later today. Okay, along with the video of the session. Okay. So I'm going to clear this in 3, 2, 1, boom. And so let's move on. And so now let's imagine that instead of having a line, now we have a disk. And so we've got the electrical field, I'm sorry, not a disk, a ring. Now we've got a ring. And the ring situation is going to be exactly the same as the line, where we are going to consider a very small portion here of the ring. That's going to be an infinitesimal part here, that we're going to consider that this is going to generate an electrical field that is going to have, that's going to be going this way. However, we're just interested in the electric part of that electrical field that's going this way. It's called EZ. Now, why? Because the same situation occurs. If I were to take another infinitesimal point here, and I were to consider that point, this point would contribute also, we would have a distance here, assuming that we're at the same distance. This would also contribute an electrical field going this way. And the horizontal components of these electrical fields would cancel out. And the only electrical fields that are contributing are the ones that are going outwards. And so this is the one we're considering. Now, for this infinitesimal point here, we find that the charge is going to be KQ. And we also have an angle here, and we're going to be considering the cosine of that angle the same way we did it previously for the same way we did it previously for the line. So we've got an angle here, and we're going to be interested in the cosine of that angle, which would be z divided by r. And we're going to have this expression where Q is the total charge. Now, here we are also going to have a certain density that's now going to be given by the area of the that's going to be calculated, I'm sorry, by the linear charge density that goes around the ring. And the only difference between the linear density of the line and the linear density of the ring is that in the case of the line, the linear density was given by Q divided by the length. Now the length is going to be the perimeter of the ring, and so we're going to have that the density, in this case lambda, is going to be given by Q, also divided by the length, but in this case the length is going to be the perimeter, which is going to be Q. How do we calculate the perimeter of the ring? It's going to be 2 times pi multiplied by the radius, and the radius in this case is given by r apostrophe. Okay. Once we substitute all of these here, we can calculate the differential, and by integrating this differential from 0 to from 0 to the perimeter, we are going to be able to get this expression in the end here, which is the total electrical field that's going to be given by the disk at this point that's located at a distance z. And here we also have a couple of problems. Now, this is going to be an additional bonus that has to do with the integral. And so for this bonus, what I'm going to ask you to find is, if we integrate this, we're going to get this expression here. And so how do we do that integral? And this one is going to be for tomorrow before midnight. Okay, so we're going to have one bonus per day. This is going to be by tomorrow before midnight. How do we solve that integral to get to this expression? And before we go and look a little bit at these problems, what would happen now that instead of looking at a ring, now we would be talking about a disk? Well, the difference with the disk is that a disk is actually a series of infinitesimal rings that are being added up to constitute a complete surface. And so basically, to be able to find the electrical field of a disk, we are going to grab the electrical field of a ring, and we're going to assume that the disk is going to be comprised by a series of infinitesimal rings. which are these. And so we're going to integrate and go from 0 to r, which is the radius of the ring. And we're going to integrate this, and we're going to get the electrical field of the complete disk, which is basically, again, taking each of the infinitesimal rings and adding all of them up. Okay. And also from here to here, we have an integral. How do we find this integral, or how do we solve that integral? This bonus is going to be for Wednesday until midnight. So you've got 3 bonuses: how to find or how to solve the integral for the line, how to solve the integral for the ring, and how to solve the integral for the disk. Line is Monday, ring is Tuesday, disk is Wednesday. These, again, turn them in via email, in solved by hand, in clear images, and the solutions to these, or the solutions to the integrals, I'm going to post them to Blackboard before the weekend, so you can compare them. But you're going to be able to do these bonuses. Okay. Now, what I want you to do for Wednesday, in the previous slide, we have a couple. In the previous slide, we had a couple of situations here, or a couple of problems having to do, similar to the other one, find the electrical field generated by a ring at a certain distance, a ring that has a certain charge at a certain distance, and also find the electrical force between the ring and a charge that's located at that point. And for the disk, there's also 2 situations here. Find the electrical field generated by a disk of certain proportions that has a certain charge, and find the force that's going to be exerted at a charge located at that point. Now, what I want you to do, we're going to solve these 4 problems on Wednesday, but I want you to try to do them. These aren't going to be to turn in. I want you to try to do them in your notes. These 4 problems of the ring and the disk, you can follow the kind of a very similar procedure with that we did with the line and the expressions that we have there. And we're going to solve them on Wednesday, but please try to do them in your notes by Wednesday, so we can compare them and we can solve them there. Okay.